Welcome. Nice to see you. You know what to do. So basically, it's something like that. A ball on a string. It doesn't have to be a minivan. It could have been any transportation device. When nothing is happening, when everything is at rest, of course, the string is vertical. But if the minivan starts moving means changes velocity from 0 to not 0 anymore. So it has to be some acceleration. And in this situation, look closely, the string is not vertical anymore. It makes a certain angle. The angle depends on the acceleration, of course, and we will calculate the acceleration related to 45 degrees angle, something like this. But the question is not about the acceleration. So eventually, the van reaches the velocity, desired velocity, and after that keeps traveling with constant velocity. So the question is about, for that situation, for that regime of the motion, when the van is traveling with constant velocity, what angle would you observe between the vertical direction and the string? And these are possible answers. A, B, C, D, E. So I'm going to start calculating acceleration, and you can keep thinking and pressing for maybe one more minute. Same set of answers. When the acceleration is not 0, that's what we observe. In this picture, by the way, what do you think is the direction of velocity of this minivan, to the right or to the left? I'm not going to ask you this question, just think about it again. Well, the velocity points to the right, and when it starts speeding up, of course, what's happening? Well, does the van touches ball? No. It's your hand, or you can attach it to the ceiling of the van. So the van itself doesn't touch the ball. What does? The string. So the ceiling of the van starts touching the top part of the string. The top part of the string starts touching the lower and the lower and the lower and the lower. So that's how eventually the ball gets affected by this motion. Of course, there has to be force of gravity acting on it, and there is a force of tension acting on it, and the angle of deflection from the vertical, this angle is 45 degrees. So it's speeding up, so the acceleration also points to the right. And of course, what you can do always is just use x and y axes and apply the Newton's law. That's straightforward calculation. Another way, which I usually suggest, is replace the angled force with its components. mathematically, of course, it's absolutely identical approach. So we got the force of gravity acting on it, and instead of actual tension force, we can use two components. T horizontal or T parallel, that's usually the name for something like that. T vertical or T perpendicular. And of course, the actual force of tension and the components of that force always make, that's vertical, that's horizontal, a right triangle. In this triangle, this angle is 45 degrees. And of course, the force of gravity must have exactly the same magnitude as this component. And according to the, well, that's the basically y component of the Newton's second law. The x component of the Newton's second law should tell us that m times a should be equal to this, the horizontal component of the tension. We've done this before, and I want to apply just to the, for the sake of review, one of the very first methods to solve a problem like that, vector addition. They're all vectors. Acceleration is a vector. So the Newton's law tells us this. M is a scalar, is just a number, positive number, the mass is never negative. But A, G, T, those are arrows, vectors. So if acceleration points to the right, MA must point to the right. That should be MA. And that should be equal to mg plus tension. And of course, when we're adding vectors, we get a triangle. Well, in this situation, again, that's a right-angled triangle. So mg plus tension equals ma. How do I know I have to start tension here and finish here? Well, my ma must, this ma arrow, this t arrow, this mg arrow, my ma arrow has to be horizontal. So if I do something like that, mg plus t, wrong, not horizontal. If I do something like this, mg t should be ma, again wrong, again not horizontal. So, and of course now we can solve this triangle. That's it. We know this angle, we know that angle. Now let's call it alpha. So mg divided by ma, if we use magnitudes of those arrows, should be equal to the tangent of that alpha. Turns out mass doesn't matter. It cancels, and we can solve it for the acceleration. Acceleration will be equal to g divided by the tangent of that angle. So from here, well, for the 45 degrees angle, tangent equals what? Thank you, exactly. So in this particular situation, the acceleration will be equal to g. And the angle will be equal to 0. Of course, when velocity is constant, there is no acceleration. When acceleration is 0, the tension, again, must cancel the gravity. Gravity points down, so tension must point up. So the string must be vertical. Any questions? These are the answers. Well, that was the last problem related to the current topic. We've learned everything on this slide, every single thing. And after having learned everything, we're going to start learning new things. Do not read this slide. So I just want to point at the fact that it looks like a lot. These are the equations we're going to talk about. We're going to use them to solve future problems. And we have to keep in mind, in our memory, everything we've learned from the past, because everything related to this topic is based on everything we've just learned. They're not, disconnected, they connected. So, of course, if you see it like that, it feels like, wow. Well, I just want to, again, remind you that everything should be seen in perspective. As future doctors, hopefully, you know that eventually you're going to memorize a lot of medical stuff, every single name for every single bone, muscle, pill, disease, treatment. So this is a drop in the bucket relative to what you're going to memorize in the future. Think about it. By the way, this comparison also tells us becoming a physicist should be easier than becoming a doctor. Maybe you should switch. And becoming a physics teacher is even easier. Well, energy. It's not, oops, wrong button. It's not easy to give a clear, direct definition of energy. So we're just going to learn how to use it, how to measure it, how to calculate it. These are the most general facts we know about energy. It cannot be destroyed or created. Well, one exception, we don't know what happened before the Big Bang. The Big Bang did happen. And after that, we believe the amount of energy in the whole universe stays the same. Where did it come from? We don't know. But now, no matter what's happening, the energy cannot be destroyed or created from nothing. It only can be, well, stored and then transferred from one object to another object, from one system to another system, from one form into another form. There are many different forms of energy. And we're going to talk about mechanical energy first. We depend on the energy. Everyone out of 7 billion people and more. The energy consumption grows up so rapidly, so it actually kind of scarier than what's happening to the climate. The population grows up, and people want to live better and better. So more and more cars, more and more TVs, more and more energy consumption. And where do we get it from? Well, unfortunately, so far, most of this goes from unrenewable sources. Gasoline, petroleum, natural gas, coal. So whether we like it or not, no matter what, eventually this stuff will be used up. So we have to be prepared. We need to think about renewables. We're going to have to use nuclear energy more. It's scary, but we don't have any choice. Thermonuclear energy. And this is what we do every day, everyone. Well, maybe not every day, if you're on diet, but still, we need energy. So we have to consume it from something, and we consume it from the food. What does it come from? into the food, normally from the sun. A single leaf is so powerful and complicated device which can absorb the energy from the sun, store it, transmit it to other parts of the plant, and then what do? And then we eat it. Or a cow eats the plant and we eat the cow. Doesn't matter. Everything happens because someone eats something. And when it gets in us, what's happening? Well, storing, sweating through, or doing something useful, what we call work. The international system of units uses a joule for the energy, but another very commonly used unit of energy is a calorie. So 1 calorie is about 4 joules. If you read on a chocolate bar, 2,000 calories times 4, almost 4.2, almost 10,000 joules. These are the forms of mechanical energy. The kinetic energy is never negative. Mass is never negative. Velocity, well, that's a vector, but if we square it, that gives a positive number. So mv squared over 2, that's what we call kinetic energy. This equation is a definition of kinetic energy. So when an object is at rest, relative to a given reference frame, it has no kinetic energy. If it's moving, it has. If it moves faster and faster, kinetic energy higher and higher. Next important kinetic energy, gravitational form of energy, gravitational potential energy, mgy. Y is that ruler we use to measure height. So potential energy, gravitational potential energy, changes when the height of an object changes. If the height is rising, gravitational potential energy increases. For the fallen object or rolling down, height decreases, potential energy, gravitational potential energy decreases. And there is one more form of potential energy, elastic potential energy. A free spring has no energy in it, but if we stretch it up, the stretch, this variable x represents the stretch or contraction, the change in the length, not the actual length, the change in it. Squared times the spring constant. We know what it is. Spring constant relates the stretch and the force. Divided by 2, that's what we call elastic potential energy. Why do we need them? Well, because they're all related to what might be happening to objects. Now, let's spend 30 seconds on this question. What do you think should be joule in terms of basic units? Where is it? Why doesn't it work? Oh, here. Okay, now. So, you know, you remember that a Newton, for example, is a composed unit. It's equal to kilogram times a meter divided by second squared. We call it a unit, that combination. Same true is for a joule. A joule is a name for a compound unit. But if we want to write it down using fundamental basic units, well, what should it be? This is a review question from the lecture number 1, right? What do we have to do? Well, we have to know the unit for each variable. The unit of mass is something. The unit of speed is something else. The unit of speed should be squared. And that should give us what joule is equal to, a joule. So that should be a kilogram times a meter over a second squared, 3. Just a review. If the speed is doubled, it's kinetic energy. All right, I'm not going to ask you to press anything. So I'm going to point at the answer. If you agree, raise your hand. Did you raise your hand? Oh, no, you're just stretching. Okay. So what about this one? You wanted to, you changed, okay. What about this one? What about this one? Absolutely, of course. Again, that's a real equation. People sometimes forget what parentheses. Yeah, we can say this is the kinetic energy number 1, and now the kinetic energy number 2 should be related to the speed, which is twice of the speed number 1. So the kinetic energy number 2 should be equal to the same mass times 2 times speed number 1 over 2 squared. And now, if you leave it like that, you answer 2, which is wrong, because parentheses meant to be there. But if the parentheses are clearly seen, visible, that gives m times 4v1 squared over 2. So that's going to be 4 times kinetic energy initial. All right, same approach. Read the question. I'm going to point at the answer, and when you agree, if you agree, you raise your hand. So this is the expression for kinetic energy, never negative. Elastic potential energy, also never negative, due to the same reasons. So what about gravitational potential energy? Eight people. More than 8 people. None? Wrong, wrong, wrong. You have to keep in mind that this is a ruler. This y variable is a ruler, and someone stole my ruler. And the ruler is what we're placing, and we can place it. How do we place things? How do we place things? If we have a ruler and we want to place it, how do we do that? Exactly. Well, it has to be vertical, but we can place it any way we like. So the 0 on the ruler could be at this level, at the level of the table, at the level of the roof, at the level of the floor. So we can start counting from any level. So it's up to us. And if we start counting from any level, the energy can be positive, the energy can be negative. So if this is my axis, and this is my 0, if an object is above 0, gravitational potential energy will be positive, but if the object is below 0, gravitational potential energy will be negative. That's it. M, positive. This is 10, 9.8, and this is what we have to measure. The actual reading on the actual ruler. And it could be anything. Moving on. Well, when we say work in real life, we mean something, well, hard, usually. In physics, the same word has a very specific meaning. Work is that quantity which changes kinetic energy. That's it. Of course, the reason for the change in the kinetic energy might be, well, vary. Kinetic energy changes if object speeding up or slowing down. Yeah. Speed changes, kinetic energy changes. So an object must have an acceleration, which means there is net force acting on it, which is not zero. Maybe one force, maybe two, maybe three. So work is something related to a force which changes kinetic energy. The unit of work is same as the unit of energy, joule. This statement has a name. We call it a work kinetic energy theorem because it, well, basically it's a law. This is the, well, shortcut word, kinetic energy theorem. And the difference between this equation and the previous one is this word, net, total. So every force acting on an object might do some work. That's it. The net force is responsible for the acceleration of an object. The net work is responsible for the change in its kinetic energy. If we have several forces, each force might do its own work. And we just have to add them up all together as numbers. Those are numbers, positive or negative. And the result gives us the net work. If net work is zero, kinetic energy doesn't change. If net work is positive, kinetic energy increases, the object speeding up. If net work is negative, kinetic energy decreases, the object is slowing down. And of course, now we have to say something about calculating this new physical quantity, which we call work. Depending on the situation, the equation might be different. This equation we always can use when work is done by a constant force. That's it. For any constant force, this is how we can calculate the work. What does it mean, constant? Well, it doesn't change neither magnitude nor direction. Both parameters of a force must stay the same. The object might be making a very complicated motion. We don't care. But if during that motion this force keeps its magnitude and direction, that's a constant force, and we can use this expression to calculate the work done by that force. And you see, this is the trajectory. The length of the trajectory has a name. We call it distance. But this arrow is not distance traveled. That's a displacement. That's just an arrow which connects initial and final locations. So this expression has three variables in it. Number one, the magnitude of this force. Number two, the magnitude of this displacement. And number three, this angle between the force and displacement. So we have 5 constant forces acting on our object. We can calculate the work for each using this expression. Then we can add them up. That will give us the total work, and that should be equal to the change in the kinetic energy of that object. You see, this expression has 2 variables which are never negative. Yeah. The magnitude of the force, never negative. The magnitude, the length of the displacement, never negative. But this parameter, cosine of an angle, could have any possible value. If the angle is less than 90, cosine is positive, work is positive. If the angle is equal to 90, if the force is perpendicular to displacement, according to this expression, that force does 0 work, doesn't do any work. If the force has an angle above 90, cosine is negative, a force like that does negative work. So a force like this tries to speed it up, a force like that tries to slow it down. Whichever wins, wins. One more definition, power. Power, it's work which being done every second. That's it. A standard unit of power is watt, which is a joule per second. But in real life, people very often use a horsepower. Horsepower is just 746 watts. And, well, distance over time is speed. So, or displacement over time is velocity. If we want to, we can use this equation to calculate the power of a constant force. Magnitude of the force, instantaneous speed, the angle between force and velocity. Work done by the force of gravity. Well, first of all, gravity does work only when object changes height. On its way up, on its way down, something sliding down the ramp or being pushed up the ramp. Whenever height changes, gravity does work. We can use this equation. Force equals mg, displacement, well, whatever displacement it is, and the angle. Mathematics, if we work it out, gives a very simple result. This is the most convenient equation for calculating work done by gravity. It's just mass of an object times g times initial height minus final height. Initial height minus final. This is what people sometimes get confused about. So again, it has to be, when calculating the work done by force of gravity, the difference should be initial height minus final. That's not the change. The change is final minus initial. But if you like change, this is how you can write it down, and this is how most of the textbooks write it down, minus mg delta y. Delta y is the change, final minus initial. Well, friction. So when one object is sliding on the surface of another, there's always friction. That's kinetic friction. Static friction doesn't do any work, right? Because there is no motion, there is no displacement. But kinetic does. And what's good about it, we can, doesn't matter how we move it, we can use the same equation for calculating work done by kinetic friction. If the trajectory is very complicated, we can just break it down into small parts. And for each small part, friction will be opposing the motion. For each small part, the angle between the force and the, well, instantaneous displacement will be equal to 180 degrees. And when we move around, the magnitude of the force of friction stays the same. It's coefficient times normal. So, and if we add up all individual distances traveled, that gives us the length of the trajectory, the total distance traveled, and cosine of 180 degrees is equal to -1. That's where this minus comes from. So this is the equation we can use for calculating work done by friction. Work done by normal force. Make your clickers ready, please, and tell me what you think. The work done by the normal force. This is an actual problem we can solve, and we will solve with a little bit more information about the mass, coefficients, and stuff. So this is exactly what I was doing just a minute ago. I was pushing this box, we know that in this situation, 4 forces acting on it: gravity, normal, friction, and applied force because of my hand. So for each force acting on this object, we can calculate the work. The work done by gravity, the work done by normal force, the work done by friction, the work done by my hand. If we add them up all together, that's what we call the net work. And that's supposed to be equal to the change in the kinetic energy of this box. What do we know about the normal force? Please, what is the definition of the normal force? Someone should say something. Definition of normal. Normal force is, there is an official definition for that force. Please. Yes. The component of the contact force perpendicular to the surface. Absolutely right. What is the most important word in that definition? No? Perpendicular. What does it mean? This word also has a meaning. So what does it mean to be perpendicular in mathematics, not in life? What does it mean? It means 90 degrees angle. And if we want to calculate the force, we have to use that angle, because that will be the angle between the force which points up and displacement. And please tell me now, what do you think about the work done by the normal force? I'm collecting again your responses to the same answer. This is a scientific experiment. The scientific experiment tells us that thinking helps. So now, you see, the distribution is very different. And now, of course, where is it here? Now, of course, we know that when calculating the work done by normal force, we should do this. Come back. The magnitude of the force times the magnitude of the displacement times cosine of 90 degrees. And cosine of 90 is 0. And it doesn't matter what displacement is equal to force, it's still going to be equal to 0. When you're multiplying by 0, the result is always 0. 0 what? Joules, that's work. So, this is how it works. See? This is how work works. This is the same slide with some specific examples. The work done by gravity can be positive or negative depending on how height changes. When the object falling down, gravity does positive work. If the object flying up, gravity does negative work. Normal force never does any work. It doesn't matter if it's an incline or wherever it is, because by definition, normal force is always perpendicular. The angle will be always equal to 90. Friction always does negative work. So this is about the difference between what do we mean by work in real life and what do we mean by work in physics. Four kilograms. It is heavy. Do I do any work? No. There is no motion. No motion, no work. But you should tell me that when I say do I do any work, I should mean force. My applied force, there is a force applied from my hand. It doesn't do any work because there is no motion. Force of gravity doesn't do any work because there is no motion. But am I, as a person, losing any energy? Yes, of course. Eventually, well, two things happen. I die or I give up. What's happening? Well, why, from a point of view of physics, no work is done, but we're losing energy? Well, because there's internal motion. Yeah. That motion also requires energy. Blood's supposed to be pumped constantly through the vessels. So we're losing energy, but from a mechanical point of view, we're not doing any work. And that person who walks with a, I don't know, baggage, wherever it is. Yeah. So displacement points to the right, but the force applied by the hand points up, perpendicular. So there is no work done by that force from a mechanical point of view. And the last equation for the work done by elastic force. So if we change the length of the spring, this is how we calculate the work done by the spring. It's very important to understand that there is work done on an object and there is work done by an object. Where's my spring? Now the spring is gone, ruler gone, spring gone. So use your imagination. I'm holding a spring, and when I'm stretching it, I'm doing a work on the spring, and the spring is doing work on me. It's like Newton's third law. Yeah? We have two forces. Forces have same magnitudes in opposite direction, and also the work done by me on the spring has same magnitude but opposite value to the work done by spring on me. This is the equation for work done by a spring on me. If I want to know the work done by me on spring, I should multiply this by -1. Flip the sign. So elastic force by spring on an object attached to it. Well, finally, first problem to solve. So what's happening? We shoot a ball. We have solved this problem before. So we know that eventually it stops. That's what we call the point of the return. That's when the maximum height is reached. And this is our initial height, and this is our final height. And we need to calculate the work done by force of gravity. And the work done by force of gravity is equal to m times g times y initial minus y final. That's the work done by gravity. Do you think it's a positive work or a negative work? Negative, of course. First of all, it slows it down, which means kinetic energy decreases, work has to be negative. Plus, of course, if you look at the picture, it goes from a low height to the high height. So this difference is negative. Well, we know the mass. In kilograms, that's going to be 0.1. We know g is about 10. All we need to know is its difference. You see, when calculating the work done by gravity, we don't need to know the exact value for potential energy. We need to know the change. So it's up to us how we choose the zero level. Always up to us. So we just, well, when calculating work done by gravity, if we want to use this equation, we always must direct the positive y direction upward. But it's up to us where we choose the zero level, the origin. Of course, the natural choice is at the lowest position. So in that case, it's going to be 0 minus y max. It stops here. That's going to be the work done by gravity. Well, all we have to do now is calculate this. That's a review question. So the fastest way to do that is applying the equation number 3, which has no name. Speed final squared should be equal to speed initial squared plus 2 times acceleration times, well, and here it's supposed to be the change, y max minus 0. And the initial speed is 20, so 20 squared divided by 20 equals y max 20. So the work in this situation done by gravity will be negative 2 joules. Any questions? Of course, we neglected friction. Otherwise, we would have to add the work done by friction, which is always negative. So work done by friction. You push a box, 4-kilogram box. You're applying force with the magnitude which is equal to 4 newtons at 60 degrees. And the static friction is so strong that you cannot move the box. So the box is at rest. The work done by friction in this situation is, if you agree with this, please raise your hand. This. So everybody who didn't show up the hand for this and for this automatically votes for this. That's what I assume. Well, it's a natural assumption, right? So static friction means no motion. No motion means which variable is equal to 0? This one. No motion, no displacement. So the right answer is 0. Okay? Moving on. Now we are applying a force strong enough, 14 newtons, to make it move. And now we need to calculate the work done by us. So again, the free body diagram shows four forces acting on this box. Well, what do we know about the work done by normal force? The work done by the normal force is 0, always 0. Now, what do we know about the work done by gravity? In general, it can be anything, but if the height doesn't change, the work done by gravity also equals 0. Now, in this situation, only 2 forces do some work. Friction does negative work, and the applied force does positive work. And this question is about calculating the work done by the applied force. So, first of all, we have to make a statement. Can we or cannot use this equation? Just a second. Yes, we can. because force is constant. So all we have to do is just multiply the force and the displacement and the cosine of the angle between the force and displacement. That's the work done by applied force. And we will pick up later on. On Monday, at first, I'm going to do the review. But what does it mean? It means I'm going to answer the questions which you have sent to me before 12 p.m. on Monday. If you don't send me any questions, I have nothing to talk about. Well, have a nice weekend. What are you looking for, eventually? I'm looking for the line velocity. Okay. No. I'm looking for the height of the door. What's your feeling? Is absolutely right way to solve it. Okay. If it didn't work, my guess would be you just made a mathematical mistake. Okay. And my suggestion is don't do it this way. Okay. There is a way which I find faster. Can I grab my pencil? Yeah. Actually, there's one here. Close this. Of course. You can take away everything. So, you know what do you know? We know the initial velocity. You know the angle? Yes. And what else? And we know the distance traveled horizontally. So if you know the initial velocity and the angle, you can calculate both components, right? So if you know the distance traveled and the x component, you can calculate the total time immediately. Because the range is equal to this component times time. So if you know the range, if you know the component, that will give you total time. And then if you know the total time, and if you know the y component, if you apply the motion equation for the y component, that should give you this immediately. You can try it right now, for example. We can meet in the resource room like in 5 minutes or so. See how it works. Yes. I don't know if you got my email regarding the exam. I'm supposed to fly out next. Right. Did you get the email? Yes, I did. Well, I did get the email. Okay. I didn't have time to think about it yet. Okay. I just wasn't quite sure. Right. I understand your situation. Okay. So your flight is on Thursday morning? Yeah, like 6:30 a.m. From the Logan? Yeah. So what's your concern? That I'm not going to get out because of the snow on Wednesday. How do you know the snow is going to be on Wednesday? There's a forecast already. Here you can take. So I thought I'd ask. How much of the snow do they forecast? My parents told me 8 to 10 inches.
again. So
And all right, let me think about it. We still have time, okay?
Thank you.
And you also should send me your complete Wednesday schedule.
Okay. I will. Thank you.
Yes. 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 You can assume any box as an individual system. It's up to us how we choose it.
But if I chose this box as a system and the normal force that I get was 32, not the...
Did you include the force acting from the top box?
Yeah.
You just have to check your calculations, I'm sure. Because if you have included all the forces, it should work for you. First of all, we have to solve two problems in one. Which do you solve? With acceleration up, with acceleration down. Acceleration points up. And which is 1 kilogram, which is 2 kilogram?
The outer box is 2.
2, 1.
Yeah.
And this acceleration has magnitude 2 meters per second squared, right? Up box, it should be 2 times 2 should be equal to force. Now for this, so that will be 4. Now for this, if we want to use this, so 2 times 2 should be equal to F minus 2 times 10. F should be equal to 24. Now here, which is 1 times 10, that force 24. You have two objects interacting right here. The force acting up from 1 times 2, down from 2 on 1. These forces must have same magnitude because of the Newton's third law. So that should be this, and this force from the floor well, we don't know yet. So that's the acceleration. Right. 1 acceleration should be equal to force up minus 10 minus 24. Don't hesitate, just if you can't ask a question personally, you can send an email